Hello, everybody. Welcome to CJ's presentation on CGA G-5 hydrogen, an American national standard. This is Rob Early, a technical manager with the Compressed Gas Association, and I'll be giving the presentation today about hydrogen and its properties. Before we get started, let's talk a little bit about the Compressed Gas Association. As you see here, CGA's mission is to provide the ever-improving safe, secure, and environmentally responsible manufacture, transportation, storage, transfilling, and disposal of industrial, medical, and food gases in their containers. And of course, hydrogen is a compressed gas that falls within that scope as well. How does CJ fulfill our mission? When we do this, as shown here on the screen, we maintain a library of more than 380 technical publications. We distribute safety information and warnings about gases in their containers. We also coordinate with other organizations to advance industry safety. We try to make sure we're working with those other groups out there. We also work at harmonizing standards globally to vary majorly between countries. We also provide technical advocacy and leadership in support of industry self-regulation, trying to write the standards to make sure what we do is safe and practical. We also develop educational materials that promote recognition and use of best safety practices. And lastly, we promote security throughout the gases industry. So that's CJ's mission, and we'll talk a little bit more about CJ publications in this one today and how to contact CJ as we get to the end of our presentation in a little bit. So today's topics, here's a list of what we will be covering today. We're going to talk a little bit about hydrogen's physical and chemical properties. We're going to talk about the proper handling and use of hydrogen. We'll be discussing the storage of gas and liquid hydrogen. Talk a little bit about hydrogen production techniques. What are some of the uses for hydrogen? How do people put it into service? Commonly used hydrogen-related terms, like a glossary or vocabulary, if you will. And last, the topic of ullage or filling space for liquid hydrogen tanks. And all this material can be found in CGA G-5. I would highly recommend you take a look at that afterwards, which expands upon what I've covered today in this presentation. But CGA G-5 is a great publication to look at. Moving along, we'll talk first of all a little bit about hydrogen's properties, and particularly the properties of gaseous hydrogen. Hydrogen is colorless, it's odorless, it's tasteless, and of course it's flammable. And we'll talk about its flammable properties in just a moment. It's the lightest of all gases. It has a 0.07 in specific gravity, meaning the weight of hydrogen is about 1/16 that of the air. So it's a very light element. There's two different types of hydrogen. This is something unique to hydrogen, not necessarily found for any of the other compressed gases. There are types of hydrogen titled ortho and para. Ortho is one where both atomic nuclei for the hydrogen for the H2 molecule. Ortho is where both the atomic nuclei spin in the same direction. Para hydrogen, on the other hand, both spin in opposite directions. So there are two different types of molecules of hydrogen. Gaseous hydrogen tends to be made up of 75% ortho and 25% para, whereas liquid hydrogen is 100% para. And that comes into effect with the liquefaction process where you need to convert ortho to para. And we'll talk a little bit more about the production process as we move along. Hydrogen also is a very flammable gas. It has a very wide range of between 4 and 75% flammable in air. And so within that range, if there's an ignition source, it can light off. The auto ignition temperature of hydrogen is about 1,050 degrees Fahrenheit, which is when it would automatically just auto ignite, if that's where the term comes from. It has an ignition energy level of about 0.02 millijoules, which is very small. So it doesn't take very much energy to light off hydrogen when you're in the flammable range. So that's one of the reasons is that you need to be very careful in dealing with hydrogen. So that's some of the properties of gaseous hydrogen. There's a couple more we'll look at on this chart. It also has a low emissivity for flame and heat radiation, so hydrogen fire does not radiate a lot of heat. You have to be pretty close to it to feel it, so you can get very close to it without even noticing it's there, as opposed to hydrocarbon fires, which have a high emissivity and a lot of radiated heat coming out from it. It also has an interesting characteristic. Normally, when you throttle gases and reduce the pressure on them, the gas goes down in temperature, as you might see from going through a control valve or regulator. The piping downstream of the regulator or control valve tends to be colder than the piping going into it. With hydrogen, the effect is actually different. Throttling the gas raises the temperature. It's just one of those unique qualities. It really has no practical impact on the use of hydrogen, but just something different about it, just something unusual you can tell your friends about. It also has a very high leakage and diffusion rate because it's such a small molecule. It will leak very easily. You may have something that's a piece of piping or a piece of equipment that you pressure tested with air or nitrogen or some other gas, and it didn't leak. You may put it in the hydrogen service and find it will leak just because it's such a small molecule and such a high rate of diffusion and leakage. Hydrogen by itself is not corrosive or reactive, so there's no corrosivity associated with it. It does have a property dealing with embrittlement. There are three types of hydrogen embrittlement, which is shown on the screen: environmental, internal, and reaction. Environmental embrittlement takes place when you have metals and alloys that are plastically deformed or bent in a high pressure hydrogen environment, just because of the environment you're in. The second type is internal hydrogen embrittlement, and this is caused by absorbing hydrogen into a metal of some sort. The last type is reaction embrittlement. This is actually where you have the same thing, absorption of hydrogen into the metal, but not only is it absorbed into the metal, but also reacts with the base alloy. So they're very similar in nature, very close, but those are the three types of embrittlement you can run into when working with gas hydrogen. So that's something we want to definitely keep in mind dealing with it. Now, liquid hydrogen shares many of the same qualities that gas hydrogen does, so we will not spend a lot of time talking about that. Basically, it's colorless, it's odorless, it's tasteless. It also is flammable when it heats up and turns into gas. It has a very low boiling point temperature at minus 423 degrees Fahrenheit. Very cold, not a whole lot of gases down at that liquid level, so it's one of the coldest ones, very close to atmospheric very close to absolute zero. It's very light as well. 1 gallon of liquid hydrogen weighs 0.59 pound, which is about 1/14 the weight of water. So just as gas hydrogen is about 1/16 the weight of air, so liquid hydrogen is about 1/14 the weight of water. So in either case, it's a very, very light element, which is something that affects the way it operates and people use it. Now let's talk for just a few moments about the production of hydrogen. There's many production techniques. There's 5 of them listed here that we will talk about just a few moments. And there are many CGA publications that cover production. We'll show you those at the end of the meeting, or the presentation, I should say. We'll run through these just very quickly here. The first one is titled Steam Methane Reforming, or SMR. This is where steam is used to reform or crack natural gas into hydrogen and carbon monoxide, which is a makeup of a natural gas. And so the plants are often called HYCO plants, for hydrogen and carbon monoxide. So these are your large industrial production plants that produce a lot of hydrogen at a time. It's also a technique called partial oxidation, which has to do with using the incomplete combustion reaction where hydrocarbons are reacted with oxygen to produce hydrogen and carbon monoxide. So it also leads you to end up with a HYCO plant. A third technique listed here is also something called autothermal reforming. And that is a combination of partial oxidation and steam methane reforming. So they're combined together to generate hydrogen. A fourth type shown here is gasification. This is where you actually inject steam into a hotbed of coal or coke to produce hydrogen. So it's gasifying and producing hydrogen that way. And the last type, which is becoming more popular nowadays because it's more of a green type of production, is water electrolysis. This is where you use electricity to separate water molecules into hydrogen and oxygen. So this is a green process, particularly when using hydroelectric generated power. And so it's one of the newer practices coming into play. And we'll talk about these a little bit further on, and also in another presentation I'll be making later on about production of hydrogen plants. So we'll move along here. Many uses are found for hydrogen, as you may well think about. When it comes to mind, probably when you talk to most people, is fuel cells for driving cars and buses and trucks. And so that's one of the great uses where hydrogen, oxygen, and air are used to create a fuel cell and produce energy for driving a vehicle. But hydrogen has many other uses. It's been around for many years, such as the synthesis of ammonia and methanol. It's also used for hydrogenating oils, although it's not done very often now because it leads to saturated fats, which are not really good for your health. Also, a specialized type of welding, oxy-hydrogen welding and cutting. Typically, this is used in underwater applications because, as I mentioned, the radiation of hydrogen is not that high, so you need to be careful need to work at it quite a bit to get the best impact. It's also actually used as a lifting medium for weather balloons. Now, oftentimes those lifting mediums for weather balloons is shown in the picture at the lower left of the picture is shown here. A lot of times they will use helium, but hydrogen can be used if done safely, and so it's finding quite a bit more use for that. It's also used in a float glass process for making very flat glass, making sure there's no imperfections in it, no changes in depth. And of course, a lot of use at NASA in particular for powering rockets, as you see in the one picture here. So it's quite a few uses for hydrogen, and people are continuing to find more and more uses as time goes by. So quite a few ways to be using it. Let's talk a little bit now about about gaseous hydrogen storage and transportation. We'll talk about ways it's stored and ways it's transported. There's three main types of equipment as shown here. One is cylinders, the smallest ones around, smallest ways of storing compared to other ones, and that's used for both transportation and storage. There's also tube trailers. They can be used for transportation and storage as well. You transport it and you park it in place and use it. And the last one we'll look at here for gas is hydrogen receivers, which is on-site storage where it doesn't move. So we'll take a quick look at these as we have a few moments to go through these. First of all, you see here a picture of cylinders. This is just an example of what cylinders look like. Typically, you see them in multiple banks of multiple receivers, which are hooked up to a manifold and sent down to the use point. And the way this is done schematically, we'll show this here, and you'll see some other schematics for the other techniques. For cylinder storage, a system will have a bunch of on-site storage cylinders, maybe a couple of banks. They're sent through a pressure regulator to knock it down to the use pressure. Go through a source valve, which isolates the storage system from the customer use. And lastly, it goes to the use point. Very simple, very basic. A lot of times in hydrogen and other gases, for that matter, as well. Cylinders are used for the first time, particularly in a lab setting where you're testing out something, trying out uses for the gas. And so cylinders are a way to go. You can transport them easily, you can set them up easily, you can swap them out. And so this is a great place for starting for using hydrogen or any other industrial gas. The next larger one on the scale is tube trailers, which is basically shown here. Trailers that are driven down the highway pulled by a tractor, of course, and you have on-site storage of high-pressure tubes or high-pressure cylinders as shown here, where hydrogen is stored and transported. Now, the way these are used at the customer site is they're actually parked as shown here. They're driven to the site, parked and left, and swapped out with the one that's sitting there. And again, the high-pressure gas comes off the tube trailer, goes to a pressure regulator, goes to a source valve, and lastly, just like the cylinders, it goes to a use point. And these are used where your volume of use goes up over time, where cylinders are just not cutting it, or you need to have more and more cylinders on site, and you're doing more and more connections, and so it just becomes a lot more activities. And so the best solution there is to bump it up to a larger on-site storage by bringing a tube trailer in. So it helps you to deal with getting more hydrogen on site and more hydrogen for your use without having to swap out all the time. The next piece of equipment shown here is on-site receivers, which look very much like the tubes that are used for tube trailers. The only difference is tube trailers use ones that are certified and designed by the Department of Transportation or DOT. On-site ones for receivers are kept permanently, and those are ASME or American Society of Mechanical Engineering standards, which apply to them. So they're hooked up on site, and the way those are used is shown on the schematic. Is a tube trailer comes on site and is actually used for delivering only. It parks by the bulk system, goes to a product transfer system, which is a valve and connections, and it fills up the on-site storage receivers. And then once the receivers are full, even they may not even be full at that time, for that matter, but the high pressure goes off and goes to a pressure regulating module, just as shown for the cylinders and for tube trailers, and it goes to the source valve and finally to a use point. So schematically, it's very similar. The only difference is now you're bringing a tube trailer on site to park it and deliver it into the tube receivers and then drive away and go back to the filling plant. So these are the ways that hydrogen is stored and delivered in a gas form. Next one we'll take a look at here is hydrogen storage and transportation in a liquid form. And there are three types of equipment we'll be looking at today. One is trailers, which are used for transportation. Another is rail cars, which are used for transportation. And lastly, liquid hydrogen tanks, which are used for storage. Here's a picture of a liquid hydrogen trailer. It's basically a liquid hydrogen storage tank on wheels, and it drives on a highway, taking it to sites where you're using more and more liquid. And the reason you might say, well, why are we using liquid versus gas? Well, over time, you may be increasing in the volume you're using, so therefore, you need more product on site. So it's much better to bring liquid on site. Liquid vaporizes and turns into gas. And a lot more a lot more gas have a liquid trailer because of that. So as your use goes up, maybe you outgrow tube trailers and outgrow receivers and switch over now to using liquid storage. There's also some deliveries by rail car. As you see here, a picture of a liquid hydrogen rail car if you're living via railways. And the third one is using liquid hydrogen tanks. These are permanently mounted on site. It's shown here with a vaporizer to convert liquid hydrogen into gaseous hydrogen and valves to control this operation. And right now we have a picture of liquid hydrogen storage. So this is how it works schematically. You bring a liquid hydrogen trailer on site, hook it up to the product transfer and deliver liquid hydrogen into the on-site liquid tank. Liquid comes out going through a product vaporizer to convert to gas. It goes through a low temperature protection module to make sure it's not too cold to impact carbon steel piping downstream. Then it has a pressure regulator and a source valve, and lastly goes to the use point. So very similar schematically to how we use gas. I mean, you basically deliver it, you send it to the customer to use it, and when the volume gets low, you fill it back up again. So those are the main ways that liquid hydrogen and gas hydrogen are used. Excuse me. Talk a few moments about cylinder storage. The cylinders are used quite a bit. You want to make sure you separate you want to separate gas hydrogen cylinders from oxygen cylinders in accordance with NFPA 2. You really don't want to have oxygen cylinders near hydrogen cylinders. You want to store away from heat sources. Don't want them getting hot and burning and flashing off. Store away from corrosive chemicals so there's no damage done to the cylinder. Store in a very secure area. Make sure to keep valve caps in place as shown on these cylinders here, that the valving is not and regulators are not exposed to damage from the outside. There's some good information about handling gas hydrogen cylinders. You want to make sure you're always using Department of Transportation or Transport Canada approved cylinders. Do not transfill from other cylinders. That's not a good idea. Any kind of piping manifold should be in compliance with NFPA 51. You obviously want to go ahead and put these into service safely, of course. Make sure you drop them off, hook them up, cage them, and do everything safely and properly. And then before moving cylinders, make sure you close the valves and put the valve cap back on top to prevent any damage from moving them. And then lastly, make sure all the connections are tight and aren't leaking. So there's a lot of cylinders being handled, so we want to make sure you're doing that properly. Hit the right button here. There's also some general guidelines to follow for hydrogen system safety. I want to make sure, in general, that these practices are kept in mind. First of all, don't have any open flames or ignition sources nearby. You don't want something burning, heating up the cylinders, heating up the receivers, heating up the tank, causing it to over pressurize and vent to the atmosphere and possibly light off. All equipment should be bonded and grounded to prevent issues from sparks or from lightning. Consider using non-sparking tools. I say consider because non-sparking tools are not always helpful. I mean, what a non-sparking tool is, it can't generate a hot spark. And so if you're using it properly, you can't create a spark that can light off hydrogen. The issue, though, is sometimes non-sparking tools are made of aluminum, bronze, manil, and they're softer, and so therefore they tend to break more easily. So you have to be careful using them. There's actually a CGA position statement that explains more about it, so that's why we say consider using it. Sometimes it makes sense, sometimes it doesn't, but it's not It's not a magic silver bullet, if you will, to take care of all the issues, but it's certainly something to be considered. And second, and nextly, of course, you want to make sure you're using the proper piping materials and techniques. It's done properly. You're not using materials such as copper, which have a low melting point. Prefer to use stainless steel in liquid service and stainless or carbon steel piping and gas service. And of course, follow NFPA2, the Hydrogen Technologies Code, which CGA has a lot of input into, and follow the CVA standards, of course. We'll talk about those in a few moments. And also, before putting anything into service, you want to definitely purge it into service and purge it out of service in accordance with CGA G-5, which is standard procedures for hydrogen supply system. And by purging it in and out of service, I mean that before you put hydrogen into a vessel, you want to make sure that you purge out all the air so you have an inert atmosphere in there. If you're purging it into service, you know, the same purging into service and out of service. If you're putting it in service, get all the air out before you fill it. Take it out of service, get all the hydrogen out of it before you send it down the road for transport to perhaps a rehab facility or a filling plant or someplace. But the goal is to make sure you're not mixing hydrogen and air when making fills or into any kind of equipment, vessels, receivers, tube trailers, tanks, anything. For liquid hydrogen, the same issues apply, of course, but you want to follow these additional techniques as shown here. One, of course, is to handle and use it in closed systems not open to the air. You really don't want to have it flashing off and creating leakage in a vapor cloud. And for that same reason, stay away from poorly ventilated spaces. You don't want to have liquid hydrogen flashing off and being in a confined space where you're surrounded by hydrogen. You want to make sure you're not in a poorly ventilated space. And you want to have that ventilation so that any hydrogen leakage and vapor can be purged away to the atmosphere and disperse upwards and disperse in a safe manner. Nextly, use any materials that are suitable for negative 423 degrees Fahrenheit, not using carbon steel in liquid service because that is not rated for that lower temperature and it will become brittle and fracture, and we don't want that. And of course, as mentioned earlier, you want to purge an inert systems before working on them. Make sure that they're not filled with a hydrogen air mixture or not filled with hydrogen either. And use classified electrical equipment that's rated for classified areas, explosion-proof equipment, intrinsically safe equipment, which is something to be very careful in using. And then the last point of this screen is, of course, to continue to purge into and out of service in accordance with H7 standard procedures for hydrogen supply system. That's a very key fact, and there's a lot of good details in H7 explaining about how that operates. So you want to handle gas hydrogen safely. You want to handle liquid hydrogen safely as well. Talk about ullage. It's a term that you probably don't use that often, but it's a liquid tank term. Really, it's used in reference to hydrogen and other cryogenic liquids. It's also called headspace. And basically what it comes down to is that ullage is the amount of a tank that you don't fill. If you have 10% ullage, it means you fill to 90%. So when you're filling a tank, you don't fill it all the way up. You fill it to some level, which is about 90% full. Typically for hydrogen and any other cryogenic fluids, the ullage rate varies between around 7 to 10%. That's typical. You might say, well, why do you do that? What's the rationale for it? Well, this really allows room for liquid expansion. As you probably know, when you fill a liquid hydrogen tank or any cryogenic liquid tank, it continues to get heat from the outside, although it takes a while to warm it up because you've got a vacuum jacketed insulation space, and so that it's like a giant thermostat. It takes a while for heat to get in, but over time, the liquid in a hydrogen tank will begin to vaporize and turn to gas. It'll start taking up more volume. The liquid will become less dense, so it'll take up more space, and eventually your liquid level in the tank is going to rise. As it rises, it gets closer to the connections for the tank safety valve and the tank rupture disc. And if something happens where a pressure relief valve opens up where the tank is almost liquid full, some of that same liquid can impact the bursting disc on the tank, and the bursting discs are not reseatable, so your tank will continue to vent until all the product is gone. So you really do not want to overfill the tank, particularly an initial fill where you're doing the filling with very cold, very dense liquid, so it takes up the least amount of space. But as it warms up, it takes more space. So you definitely want to have some kind of room. And G5 explains quite a bit about ullage, gives some more details about it, some of the mathematics behind it. And I would encourage you to take a look at that for your own knowledge to find out more about how ullage works for a liquid hydrogen tank. Last part of CGA G5 is common terminology. And typically, a CJ standard will have a glossary of terms that are used throughout the publication. What we've done in G5 is actually put together some common terms that are used in the hydrogen space that may or may not be mentioned in this publication, but they're put there as a good guidance to you. So if you're new to the hydrogen space and wondering what some of these terms mean, I would highly encourage you to take a look at G5 and there the terms are, and they should be a great help to you to find out what people are talking about, including terms like ullage. And just for some more information, because we did just a quick run through of G5 today, there's some other CJ hydrogen publications I would certainly point you to looking at. One, and they're listed here. And I will do a quick run through of them. G53 is a commodity spec, what the QA, what the quality assurance methods are for looking at it, what kind of content, what kind of impurities are allowed for both gaseous and liquid hydrogen. So I would encourage you to take a look at that. G54 covers hydrogen piping at user locations and gives you some good guidance on what to use. It's a good supplement to the piping codes and standards. G55 is a standard for hydrogen vent systems that explains the proper way of putting in vent stacks to pipe safety valves and vent valves too for venting to the outside in a safe manner at a good location at a high enough elevation. H3 is a standard for cryogenic hydrogen storage. It's basically a standard for the liquid hydrogen storage tanks that we discussed earlier in this presentation. H5 is a standard for bulk hydrogen supply system. This gives you all the details for what you're putting in, how to design a bulk system, how to install it, how to test it, how to maintain it, and how to take it out of service. So it's a good start to finish publication for hydrogen systems that are either gas or liquid, can be either one. And then H7 we mentioned earlier is standard procedures for hydrogen supply systems. And so some of those procedures cover purging into and out of service, and also have some other good standard practices used for putting in hydrogen supply system. H17 is a guideline for small scale hydrogen production. This covers the various techniques of hydrogen production. And so if you're interested in a good overview of hydrogen production techniques, I would encourage you to take a look at H17. It gives you all those details in a quite encompassing document. And the last one we have listed here is CJ Position Statement 55. It tells more about non-sparking tools, gives you some good guidance about when non-sparking tools are a good idea, when they're maybe not the best idea, so you can find out more about it by turning to that standard. And there's also some other additional resources shown here. You can find it from CJ by going to cjanet.com. It lists a lot about what CJ is doing, lists events coming up, training, has links to all the publications we have, to training modules, to anything else that deals with all the compressed gases, not just hydrogen. But you can certainly find out a lot there. For something that's more focused on hydrogen, you can go to the Safe Hydrogen Project. It's shown in the middle part on the right side. That has a lot of details about hydrogen itself, points to the standards, points to some snackable content online to find out more about hydrogen systems. And by snackable content, we mean just very brief material, maybe 2 or 3 minutes total, explaining a concept such as venting, roofing over hydrogen systems, things of that sort. So you can find a lot of that on there as well. And then, of course, h2safety.info is another good resource for hydrogen details. So I'd encourage you to take a look at that. There's a lot of details about hydrogen safety at CJ's website. And last, it's been my pleasure to talk to you all today. Hope you've learned something from it. Certainly would encourage you to contact me if you'd like. I have my email address listed there, my phone number, my LinkedIn profile. So glad to take any questions I can answer from you. And feel free to reach out at any time. So thank you again. It's been my pleasure speaking to you all today.